So I'm starting the recording now, and we'll get started. So today's work finishes out the little bit that we've been doing on electrochemistry. And one of the things that you're going to see is that we're going to make a connection between equilibrium and electrochemistry and Gibbs Free Energy and electrochemistry. And we've already made a connection between Gibbs Free Energy and equilibrium. So basically, this is a little triangle of connections. Your book actually makes use of that graphic, which I think is really cool. And then you're going to see some non-standard states that go along with this. So that is, what does this all look like when we're using different concentrations of things? So again, it'll be a really neat thing to look at. And like I said, this is one of the areas in science that is like really kind of growing and booming because there's a need for mobile power, and batteries are a big part of that. So if you can be on the team that works on some of these things, that develops things that will last a very long time, fuel cells in space, down to cell phones that will keep their charge for a full day like the manufacturers said they would 3 years ago. So it's a big field. You're going to want to, this is something that I think is foundational. So that said, let me go ahead and start sharing the screen. Here we go. And laser my pointer. Okay, so today for class, Gibbs Free Energy, equilibrium, batteries, and corrosion. The batteries and corrosion part are sort of like applications of things. And then important dates for this week, your last quiz for the semester, right, is this Thursday. It'll be open from 12:01 to 11:59, just like they all are. Your extra credits due Friday, and your homework is due Sunday. So all of those things coming up, and then we'll have our next exam next week. So, cell potential relationship. So we've been spending a lot of time on these two things for like the first big portion of the semester. This has been like an add-on for the final third of the semester. And it turns out that this has a relationship to both of these things. So we're going to take a look at what those is. So for a spontaneous cell, we say that the cell's potential is equal to the reduction potential at the cathode minus the reduction potential at the anode. So if that is positive, if Ecell is positive, that means that electrons will flow freely from the anode, where oxidation is taking place, to the cathode, where reduction is taking place. So electrons will go from this one to that one. But there must be other relationshiip, right? One of the things that we are aware of is that for something that is spontaneous, Gibbs free energy, or delta G, is less than 0, and Ecell is greater than 0, and K is greater than 1. Now, K being greater than 1, it does have a role to play in spontaneity, but what that really means to us, taken by itself, is that the reaction that goes favors the product side, which we're saying is spontaneous in the forward direction. Okay, so this equation is one that comes forward. Your book actually goes through a little derivation of it, which is not a bad thing at all. It's just something I can refer you to your book for, as opposed to that. So we'll just get to the final point right here. So the Gibbs free energy is equal to negative NFE, where N is the number of moles of electrons that are exchanged in a reaction. F is what's known as Faraday's constant, and E naught cell is E naught cell. Faraday's constant has this value, 96,485 coulombs per mole. So if E cell ends up being positive, which we say is a spontaneous cell in the forward direction, multiplied by F, multiplied by N, and we take the negative of that, these are all positive numbers, 3 positive numbers. The negative of that will be negative. So E cell is positive, delta G would be negative, it's spontaneous. And this is just kind of how E ends up being calculated. So we have potential difference in joules and charge right here. So how would we determine the delta G naught for this reaction? And is it spontaneous or not? So what we have here is water being added to sodium, producing hydrogen gas and hydroxide, and 2 sodium ions. So is this spontaneous? How do we figure this out? Well, let's break it up into its 2 half reactions. So on this side, we've got sodium, And on this side, we have sodium plus. That means it's being oxidized. It goes from a 0 to a +1 charge. There are 2 of them. It ends up giving off 2 electrons. There are 2 waters, making hydrogen gas and 2 hydroxides. And that is a gain of 2 electrons. This is the reduction. So we've broken it up into the 2 potentials. So I go to that table that's in your book, and I look up the E values for both of those. Okay? Next thing we do is we need to figure out which one of these is the cathode, which one is the anode. So the cathode is the one where electrons are on the reactant side, because this is reduction, cathode. And then the anode side is where electrons are on the product side, because it's oxidation. So Ecell is equal to E cathode minus E anode, which is -0.83 minus -2.71. And so we end up getting positive 1.88 volts. Okay, so that's the Ecell. That is not the delta G, that is the Ecell. But we need this number in order to get delta G. So here's our equation for finding delta G, and that's equal to negative NFE cell. And I just sort of plug in these things here, 2 from the number of electrons that are being exchanged. Faraday's constant, always a constant, and then the Ecell. So basically we go through, a calculator gives me this, and then with the right number of significant figures, which is about 3, then I'm allowed to be here. Any questions on how that one gets solved? It's actually relatively straightforward as long as you can get through this first step, determining what Ecell is. Any questions on that? Okay, we'll move on. So we think about this. Is this spontaneous? So I've got iodine and 2 bromides going to 2 iodides and a bromine. And for my bromine reduction potential, this is being oxidized, so oxidizing bromides to bromine gets me, is 1.09. And reducing my iodines to iodide is 0.54. So the Ecell for this is negative 0.55 volts. Negative. Is it spontaneous? So my delta G is a positive 1.55 times 10 to the 5th joules, using the equation we just used. So is this spontaneous? Well, G is positive, so it's not. Not spontaneous at all. But if you take a look at the E naughts, because this one is a larger and more positive one, in terms of its reduction potential, it is not, really all that favorable. So if an electron is available, bromine is much more likely to take it than iodine is. So if there's an electron available, this is going to take it more than this stuff will end up taking it. So as written, this is backwards. This reaction will not go forward. So bromine is more electronegative than iodine, which means that bromide is more stable than iodine. It might have been first semester, you guys worked on a lab where you had sort of bromine and hexane, and you would shake these things and look for color changes and use that to determine an activity series. This is based on exactly that. So as we go down the periodic table, things can get a little bit more oxidizing, and as we go up the periodic table towards fluorine, they're better oxidizing agents. That is, fluorine really wants to be reduced, okay, more so than some of these other guys. So it's one of these things where you can start to actually look at molecular trends, atomic trends, and use that to justify some of the math that you're doing. So let's look at Ecell and equilibrium. This is a connection between the equilibrium state and the cell potential for our state. So remember, if Ecell is positive, G naught is negative, or delta G naught is negative, and K is greater than 1. So since we have this expression for delta G, RT natural log of K, when we substitute in this, Ecell is equal to RT NF natural log of K, one of the expressions that we had used previously. We can simplify it to this expression that is here in red. Okay. And one of the things you might notice is that we had natural log here, and here we have log base 10. So anytime you see log log, that means log base with a base of 10. This is log with a base of Euler's number E. And there is a numerical conversion between the two. And that plays out in how we get this number here, 0.0592. Now, the other things that we have here, at a certain temperature, 25 degrees Celsius, R being a constant and F being a constant, these three things plus the conversion to ln get us to this number, 0.0592. All right, so on a typical quiz or test that's standardized, you would be given this information. This would be an equation that's just sort of given. So again, this connects us between the equilibrium state of something and its Ecell. So if K is greater than 1, if this number is bigger than 1, then Ecell is positive, because the log of numbers that are greater than 1 is a positive number. But if K is less than 1, the log of a number that is less than 1 is a negative number. So Ecell becomes negative, which means that this would not be spontaneous in the forward direction. It means that reactants would be favored, not products. So you can kind of like follow the math in your head and see where it gets you there. And now we've got this big 3 connection, right? So we've got an Ecell, we've got a delta G naught, and we've got a K, and we've got these wonderful little expressions that tell us a little bit about what ends up happening for each one. So the expression to go between Ecell and K is this one. The expression between delta G and K is this one. The expression between delta G and E naught cell is this one. Okay, so we've got this wonderful trio of relationships here, which means that we can use that to do some problems. And so let's say we want to determine the equilibrium constant K in delta G for the oxidation of iron. So iron going from a 0 oxidation state to a +3 oxidation state. All right, and hydrogen going to a 0. So there's a few things we're going to want to do in order to do this. First, we need to determine the value of Ecell. That will allow us to plug a number in here. These two are constants, and we can get delta G from that. And then from that number, we can use this expression to get to K, or we can use our Ecell to get this number. So knowing just one of these means we can get the other two. So let's determine K and delta G for this reaction. So I've rewritten it here. So what I've done is I've separated this out into its oxidation reaction and its reduction reaction. There's two things here. Iron solid going to iron 3+, and a total of 6 electrons are being given off here. So there's 3 electrons being given off for every mole of iron. 2 moles of iron are being reacted here, so 6 electrons. And then this one here, 6 hydrogens plus 6 electrons goes to make 3 hydrogens. Gases, 3 H2 gases. When I look up the E values for these, this E is negative 0.036, and then this is the standard hydrogen electrode, SHE, so that is 0. And you would find both of those on that page in your textbook, which is not sitting near me right now, but you know the one you can look it up on. Okay. So Ecell is equal to EC minus EA, so 0 minus negative 0.036 brings us positive 0.036. This is a spontaneous reaction, and not a giant surprise, because we know that iron rusts, right? It turns into iron oxide relatively easily, right? This is a slightly positive voltage here, so over time, iron will always do this. So the delta G for this, N times F times Ecell, so N is 6 here. Now we don't go through and divide this by 2. 6 electrons are being exchanged between these two. All right, so we've got 6 electrons being exchanged. So 6 is our value of N, Faraday's constant, and then the value of E. Plugging that in, we get this, and then we're allowed to keep the two significant figures. So negative 21 kilojoules. Okay, so this is a number in joules, and then we can convert it to kilojoules here. So iron is spontaneously oxidizing. We kind of knew that. Now let's get the K value for this. So if we know the Ecell value, which we just calculated, we just plug in the N and we can solve for K. So 0.036, here is our Faraday's constant over 6, or not Faraday's constant, 0.0592 over 6. And then solving that, multiplying by 6, dividing by this, and then taking the antilog, we get 4453, which comes closer to 4500. Okay? So not that bad. Really, it's just knowing what equations to use. And really, the thing that requires the most critical thinking is this bit up here, which is trying to make sure you've got the right expressions for your oxidation and reduction potentials. Before I move on to the next slide, any quick questions from you guys that are here with me? Anything you want explained on this? Okay, I'll move on. Question in the chat, perhaps? Where does the 0.0592 come from? So that question comes from Anne. All right, Anne. It's actually just in the expression right there. Because R, T, and F, R being the universal gas constant, T being the temperature, and F being Faraday's constant, they are all numbers. This number kind of comes from all of those being multiplied together. It doesn't change. Okay, I hope that helps explain where that number comes from. It's not one that we calculate. It's one that's kind of just given to us in the equation. Good, I'm glad that helped. Okay, E0 cell and E cell. Now, when you're, I don't know, when you're a teacher like me and you're going through and doing these things in PowerPoints and stuff, it can be rather frustrating because if you don't put this 0 here, this what we call not, it means that you might be working with something called E cell, which is different from E0 cell. These are two fundamentally different things. And so I'm going to try to explain the difference between the two of them because it's an important difference. So for E0 cell, it means that everything that is part of that reaction is in its standard state, which means that if it's a gas, it's at 1 atmosphere. And it's at 25 degrees Celsius if it's a gas, or if it's in a liquid state or an aqueous state. And if it's a solution, its concentration is 1 molar. So that's what E0 cell means. It means that all of these things are in their standard states. You have to excuse me 1 second. My neighbor's kid's coming over to see if my kid can play. My kid's not home. Gibbs not home from camp yet. So maybe when he comes along, okay? Ready? Yeah, he's from camp this week. Okay, see ya. Bye-bye. All right, sorry about that, guys. All right, so all those standard states. Now in the Ecell, basically all the same species are present, but at least one of these things has changed. Concentrations and temperatures, pressures may vary. So typically what we're going to deal with are changes in these, in concentration or in pressure. Those two things, because they tell us about the different numbers of particles present. This can change as well, but it does cause some other things to change. It's a little beyond what we kind of want to do in a class like ours. So these are the two things we would really worry about changing. So what an E-cell represents is non-standard states for a reaction. And so how do we determine the potential under a non-standard condition? So here's our delta G equation. And this is an equation that we introduced before. So delta G at standard states minus RT ln Q. That is, remember delta G had this value of 0 anytime that we are not at equilibrium. Or anytime we are at equilibrium, because that means that we're not progressing the reaction in any direction. And so we've got this little like corrective value, RT natural log of Q. So that's why we have Q here instead of K. So Q is the concentration ratio under non-equilibrium conditions. If we're approaching equilibrium from either side, the product side or the reactant side, you know, we've got this sort of like U-shaped curve. That means that we're approaching equilibrium, and this will become 0 at some point. If we substitute in the NFE portion, so delta G equals NFE, and we just sort of went over that, for a cell and for E not cell, so standard conditions, non-standard conditions, minus this RT ln Q. We do some rearranging. R and F are constants, and the temperature is 25 degrees Celsius. So that brings us to what's known as the Nernst equation, basically dividing everything here through by N and F. Okay, and again, here we have that number 0.0592 popping up where we go from natural log to log base 10. And this is what's known as the Nernst equation. So that means that the standard cell potentials, right, that we get off the table minus this number, which often, the whole product here ought to be relatively small, 0.0592, over the number of electrons being exchanged times the log of Q. That will get us Ecell. So usually this number is a little different from this one. And you can think about it like this. When your cell phone has been plugged in all night, it means that you've got a full battery. And your battery gets used up as you use your cell phone, or as it does things for you throughout the day. By the end of the day, it kind of needs to be plugged in again. So batteries don't ever really go dead. They go towards equilibrium. So that means that this Ecell and E0 cell get further and further apart the more a reaction progresses towards an equilibrium. So under standard conditions, Q is equal to 1. Ecell is equal to E0 cell. When Q is less than 1, Ecell is greater than E0 cell. When Q is greater than 1, Ecell is less than E0 cell. Okay, so that all has to do with the fact that we've got this negative sign here. So when this number is less than 1, this whole thing is negative, which means that you're subtracting a negative is like adding a positive. That makes this number bigger. If this number is greater than 1, like more towards the product side of things, this becomes a large negative number. Subtracted from this, this becomes a smaller number. So just understanding how the math impacts this is always a good thing to think about. At equilibrium, Q is equal to K. And at equilibrium, Ecell is equal to 0, meaning that we no longer really have the free exchange of electrons. Things have equilibrated. They're not doing anything anymore. And that's what happens when you run out of battery. Your phone has equilibrated, right? So every battery kind of works on this separation of charge idea. And over time, charge goes from one thing to the other and does work. So you get to do all your fun apps and Snapshoots and stuff like that. And then at the end of the day, we need to restore it to its original state. So we plug it in, and then that forces charge to go in the opposite direction until it's full. Unplug it, and start your day again. So I always thought that was sort of a neat thing to think about. All batteries, no matter what it is they do, work like that. Okay, so there is this neat idea based on that kind of thing of a non-standard cell that's called a concentration cell. And a concentration cell works like this. You've got a regular cell set up, except you've got the same thing on both sides. So here I've got a piece of copper sitting in a solution of copper 2+. And over here, I've got a piece of copper sitting in a solution of copper 2+. And I've got a salt bridge between the two. And I've got a little meter telling me how many electrons are going between them, or what the charge difference between these two things is. And it turns out that if the concentrations in both of these things are equal, right now they both equal 1 molar, no electrons move from one side to the other. Everything is equal. This is equilibrated. So nothing's going on. So in a concentration cell, what happens is we will make one of these more concentrated than the other. So this one here, this has a concentration of 2 molar. This has a concentration of 0.01 molar. That means that this side right here does not have enough copper 2+ ions, and this has too many. So these need to start being reduced, and this copper here needs to start oxidizing itself to increase the number of these ions. So this becomes an anode. And this becomes a cathode. Even though the same species are in both of these, they're not there in the same amounts. So electrons start, going from this side to that side. So now we have like a noticeable Ecell, right? And if we watched it for long enough, this copper right here would end up weighing a little bit less. This copper right here would end up weighing a little bit more because we got to take ions out of solution here, and then we got to put ions into solution here. So this is an actual functioning cell. So we should be able to figure out what an Ecell for a non-standard cell is. So here is our Nernst equation. Ecell is equal to E0 cell minus 0.0592 over N times log of Q. So in this particular instance, Q is basically our anode over our cathode, or whatever's on our reactant side going to our product side. So 0.01 divided by 2. So we just sort of plug that in here for this Q. Now there are 2 electrons being exchanged here. That's what this N represents, and so that's where 2 comes from. how did this E cell or E naught cell become 0? Well, at standard conditions, which is what this is, we have the same concentration of copper on both sides, and the value there is 0. It's an automatic 0. So this is automatically 0 for us. Don't have to measure it or anything. It just is 0. We don't have ions moving. We don't have electrons moving. So nothing is happening there. Okay? So we just sort of plug and chug, and we get this value of 0.068 volts. And the bigger the difference in those concentrations, the larger this number becomes. So again, here we've got our Nernst equation, and that is the E naught cell, which means that the low concentration side is sending electrons to the high concentration side. It's spontaneous. So this reaction ends up taking place on this side, creating more copper ions. And then the high concentration side gets reduced because it's receiving electrons. So this is the reaction that's taking place. Copper ions are getting those electrons and turning into copper solid. And this will continue until they have the same concentration. Now, as this goes on, this concentration is continually changing. So this number right here isn't always going to be the same. You get what's called an initial value, and then over time, that value changes. So it's a neat thing for us to pay attention to. So I've posed it here as a question. This is a question that comes right out of our textbook. I believe this is number 77, which is good because it's got answers in the back, and you can take a look at those. So we've got a voltaic cell that has solid zinc on one side becoming zinc ions, and then solid nickel on the other side becoming nickel ions. And the initial concentrations are nickel is 1.5 molar and zinc is 0.1 molar. So what is the initial cell potential? What's the cell potential when nickel has fallen to 0.5 molar? And what is the concentration of nickel and zinc when I've got a 0.45 value for E cell? 3 different questions here. So let's take them one at a time. First, that I think that it's helpful to realize is, well, what the heck is going on? So zinc solid is being oxidized to make zinc ions, and then nickel ions are becoming nickel solid. So here's my oxidation. Here's my reduction. Okay, and this would have a positive E cell. So my Q is going to end up being my products over my reactants. Okay, oxidized over reduced. So I'll figure out my E cell here. So this is my cell reduction, my reduction potential for zinc, negative 0.76. This is my one for nickel, negative 0.23. This is my reduction. This is my oxidation. So it's this one minus that one. Answer the question here. How do you know which is oxidized and which is reduced? So a good question from Nicole. How do I know which one's oxidized, which one's reduced? Looking at the reaction this way you can tell, but what if you had accidentally set it up so that it was nickel solid plus zinc 2 plus going to zinc solid and nickel 2 plus? What if you had done it in reverse? If you had done it in reverse, these two things would be reversed, and this would be a negative number. And if that's the case, it's not spontaneous. So looking at the reduction potentials is what helps you figure out which way this is going to go. So I looked at the reduction potentials, and then I wrote this equation based on that. All right, you're welcome. It becomes a little more obvious when you try a couple of these. I don't think that was the greatest explanation for anything I've ever given, but I do think that if you follow along and you try some of these, you might get used to the progress. You can sort of see that this can only go one of 2 ways, like in this direction or in the backwards direction. And if you write it in this direction, your E cell comes out positive. If you write it in the backwards direction, it comes out negative. You need the one that's positive. If it was electrolytic, it would be reversed. Correct. So that isn't a topic that I've hit on yet, but you're right, Curlis. If this was electrolysis, we could run it in the reverse direction, but that means we're giving it energy. We haven't covered that yet, but yes, you're right. Okay, so back to this. So figure out the initial value of E cell. So here's my standard state reduction potential. So that is my E naught cell. All right, so I'm plugging this into the Nernst equation. So 0.53 minus 0.05292 over 2, and then log of my zinc concentration over my nickel concentration, and that whole thing gets me 0.56. So it stays on the positive side, which means that over time my nickel concentration should be dropping and my zinc concentration should be rising. So the second question, what is the cell potential when nickel 2+ has fallen to 0.5 molar? So here's how that looks. If nickel goes from 1.5 molar to 0.5 molar, it's a change of 1 molar. That means zinc is going to go up by 1 molar. And so I wrote that out here. So zinc would go from 0.1 to, not to 1.0, to 1.1, not 1.0. That should be a 1 right there. That'll be fixed in the, that'll be fixed when I end up posting this. So for those of you watching this, this should be 1.1, not 0.1, not 1.0, 1.1. I have it fixed here. So it's the right number there. So my E0 cell becomes 0.0592 over 2, log of 1.1 over 0.5, and my potential becomes 0.52. When this reaches equilibrium, remember my potential would be 0. Okay, so I could see that as the concentration of this changes, it's getting closer and closer to this being 0. It just dropped by a little bit. Okay, the last question, number 3, what are the concentrations of nickel 2+ and zinc 2+ when the potential is 0.45? In this situation, I know what the Ecell is, and I need to get what this ratio is. So here is basically how it looks. 0.45 equals my E0 cell, negative 0.0592 over 2. Log of, here's my zinc concentration, 0.1 plus some amount. And my nickel concentration is 1.5 minus some amount. Because it's a 1-to-1 ratio, these things are the same. So I just need to figure out what the amount is. So all I need to do now, basically this is a lot of simplification all in one step. Subtracted 0.53 from both sides, multiplied both sides by 2, divided both sides by negative 0.0592, and took the anti-log of that. So basically a lot of simplification steps going from this step to this step. But now I can multiply both sides by 1.5 minus x, which gives me this. And then I've got 0.1 plus x on the other side. And my x turns out to be 1.4968. Okay, very close to 1.5. So all I need to do to figure out my zinc concentration is take this number and add it to 0.1, which comes out to 1.59, which is basically 1.6. And my nickel concentration, 1.5 minus this number, gets me to about 0.003. Now this is one significant figure past what we would normally keep. In this case, we're making the exception because this number is not 0 when we're done. So we're there. So basically, this gets pretty close to an equilibrium number when I have almost all zinc and no nickel left. So the last question there was a little bit tricky because you could probably see a relatively easy way for you to get to this Q number here, but how do you get the two concentrations? You need to realize that it's the concentration you started with plus some change, and the concentration you started with minus some change, and you end up getting there. So that's the real cognitive leap. And if you're going to pay attention to something in this particular exercise, this is the bit to pay attention to right here. See if you can see where this came from. We started with 0.1 molar zinc. Some amount of it was being made. We started with 1.5 molar nickel. Some amount of it was being consumed. Our job was to find the amount and then go from there. Okay. So here, this one was tricky. I did this wrong once and then right. So the KSP, and this is the last of the concentration cell ones that we do. And this is actually, to me, one of the neater ways that you can engage this, and I'll explain it as we go through the solution. So copper 1 iodide 1.1 times has a KSP of 1.1 times 10 to the minus 12. I need to find the Ecell for it in this reaction. Okay? So I've got, and they did it in a shorthand, or I did it in a shorthand. Now again, this comes to us right from the book. This, I believe, is question 119. So this is what the electrode is, and I've got this solid there on the inside, and this is the solution it's sitting in, iodide solution. On the other side, I've got a copper 1 solution, and there's a copper electrode sitting in there. So that's kind of what it looks like. I've got one cell here. It's got an iodide solution that has a concentration of 0.1 molar. On the other side, I've got a copper 1 solution that has a concentration of 1 molar. I've got a, a copper electrode connected to a wire to another copper electrode. And then to this one, we've added a little copper iodide. And basically what I'm trying to figure out is, how soluble is this copper iodide? Or how many copper ions go into this solution? I'm given the KSP in this situation, okay? Copper iodide solid is what's formed here, and it's not very soluble. So remember, the KSP for something is equal to the product of the equilibrium concentrations of the two things that we have, copper and iodide. Your first instinct, and mine was, is to say, okay, both of these are X, and it must be the square root of this. It's not quite it. What I'm dealing with is copper iodide breaking up into these two things, and I've got this sitting in a solution of iodine. That is why I felt it was important to draw this. If I drew this, then I got the clear picture that this copper iodide was sitting in a solution of iodine. So the initial concentration of iodine was 0.1 molar and not 0. Hopefully you see where that comes from. The next thing we're going to do is we're going to, allow some of this to dissolve. So some copper ions form, some iodide ions form. And so at equilibrium, I've got some copper ions, and then I've got 0.1 plus some iodide ions. So my expression is really X times 0.1 plus X. I want to solve for X. But I'd have to use a quadratic to do that, and that's a lot of work. So I'm going to do the small x approximation. So this becomes X times 0.1. And X becomes 1.1 times 10 to the minus 11. Okay? So now I've got a concentration of copper. So what that really means is my copper concentration on this side is 1.1 times 10 to the minus 11. And on this side, it's 1. So now it's just a concentration cell. So Ecell is equal to E naught cell minus 0.0592 over 1, not 2, over 1. The reason it's 1 is because only one electron is being exchanged between copper and copper 1 plus. So it's copper 1. Log of 1.1 times 10 to the minus 11 over 1. That's the concentration on this side. 1's the concentration on this side, so that's where those two numbers come from. My E naught cell is 0, don't forget. Okay, so at standard states, if I had 1 molar on this side and 1 molar on this side, my E cell is 0. So that would be E naught of 0. And then this all becomes, when I do the math, running through my calculator, this becomes negative 0.65. So 0 minus negative 0.65 is 0.65 volts. And so that's the answer that I would actually get for this one. This is question 119 in your text. And it's one that's worth looking at. So if you go to the back of the book and you look at this, for that one, they give you a different concentration of iodide, though. I think it's 1 molar as opposed to 0.1. The process would still be the same. Okay, so your book at this point, I would have gone into electrolysis, but they're doing batteries now. So we're all familiar with these kinds of batteries, these AA, AAA type batteries. And if you were to cut one open with a saw, which I do not recommend doing, there's all kinds of stuff there on the inside that really should stay on the inside. There's two things here. So you always notice there's like a plus side and a minus side to these batteries. The positive terminal is where we sort of have some reduction taking place, and then our other terminal here is our negative, so we have some reduction, oxidation taking place there. So there's a graphite rod here in the center, and then what they call a moist paste. So if these things ever go bad, that paste kind of like expands and comes out, and you see like crust around here. That's what a lot of this is, containing manganese 4 oxide and ammonium chloride. And this is part of the reaction that ends up taking place there. Usually there's zinc there on the inside, and so this is what's going on the anode, this is what's going on the cathode, and this produces, and if you look at the side of the battery, it actually tells you about 1.5 volts, and if you put two together, that's like 3 volts. And often that can be enough to run a lot of like electronics that you're used to using. You know, this would be about a 6 volt or so. Most electronics that you use, like your phones and watches and whatnot, need at least 5 volts to run, 4.5 to 5 volts. This would be about 6, these batteries added up. And it runs. You might need something a little more oomph, like your car, or some other very long-term functioning batteries. So there's what's known as a lead acid battery. And these can be 6 volt or 8 or 12 volt type batteries. And here you've got, it's lead at the anode and lead at the cathode. So you've got a couple different oxidation states of lead. So I've got lead 0 going to 2+ and lead 4+ right here going to another oxidation state. Oh no, here we've got the water tunes. I'm sorry, lead 4+ going to lead 8. I can't, something's odd about this part. I need to revisit this one. This is exactly what I got. At any rate, you have an anode and a cathode here, and this produces about 2 volts. 6 of these plates are in series, and one of the products of this is sulfuric acid. So your car will continually run through this and then recharge it, and run through it and then recharge it. So the job of the alternator in your car is to recharge this battery. And you've got this, one of the things that'll happen is like water will be consumed in this process. So every now and again, when your battery gets checked, we'll add some water to it. But these can be fairly challenging to work with. You really want to be careful around these sort of 12 volt batteries. The future, however, especially in space travel, is the hydrogen-oxygen fuel cell. So you've got an anode here where we've got hydrogen going to make water, and we've got oxygen going to make hydroxide. So we've got an oxidation and reduction here, and the overall reaction is this hydrogen and oxygen going to make water. So the cool thing about this, like if you, some cars have been trying to move towards using water as the only thing that actually gets expelled. Right now, our cars expel a whole lot of carbon dioxide and some other stuff like soot. Not great for the environment. Water much better for the environment. Well, there are no hydrogen filling stations around, even though some, if you look at brand new cars on Toyota's line or some of the others, they are marketing at least some of these hydrogen fueled cars. So in space where there is abundant hydrogen, although really it's rather far apart, these fuel cells can actually last for a very long time, and they produce water as their only byproduct, and then astronauts can actually drink this water. So this is part of the water regeneration process that they use in space. So fuel cells like this are part of the future, and electrical current actually will come out of this rather spontaneously. So it's a cool way to go. Now this is what Kyrillos was talking about, non-spontaneous electrochemistry, called electrolysis. And so electrolysis is a reaction that instead of producing electricity by running forward in the forward direction spontaneously, this is one that requires electricity to go in the forward direction. And it won't be spontaneous because it requires electricity. So if we put electricity in, then something will happen. And so this is very common with electroplating. This is a really fascinating thing. We don't have the time to get into it in the detail that would really be necessary. So this is a very hand-wavy way of going through it. But the idea is that this reaction uses electricity to drive a non-spontaneous reaction, and we can plate various metals with it. And so most jewelries, if it's not a solid gold ring or a solid platinum ring, there's nothing in this particular ring but platinum, but there are some other things that might be made that are like maybe zinc on the inside, but platinum or something else on the outside. A lot of materials get made through a process like this. Certainly a lot of circuits are made using a process like this, electrolysis. You can actually do this in your home. You can use a couple of pencils, some batteries, and water to make hydrogen and oxygen gas. I'm planning on doing that soon. So a voltaic cell is one where I've got like zinc on this side, copper on this side, and because of the way that it's set up, I'm going to produce a current that goes from one to the other, and I'm going to have 1.10 volt separation. An electrolytic cell would make this go in the opposite direction. So cathodes and anodes would switch. So right now this is being oxidized, making more zinc ions. So this is being reduced, getting fewer copper ions. This is, the opposite would be that I am consuming copper ions no, I'm sorry, creating copper ions, making this the anode, and then consuming zinc ions, making this the cathode. So by putting a voltage source in here that is greater than 1 volt, 1.1 volts, I can make this run backwards, and that's what an electrolytic cell would do. Now, corrosion, changing back to things that are spontaneous, this is a spontaneous chemical reaction, and we've all seen signs of it. Iron rusting, basically, is what corrosion is. So it's a gradual and typically unwanted oxidation of metals that are exposed to the environment. They're exposed to the sun and the wind and the rain and everything else that goes with it. And so oxygen is really good at being reduced, which means it's really good at oxidizing other things. So we have oxygen going to make hydroxide. And then in the case, if there is acid around, oxygen in the presence of any kind of acid, when we have acid rain currently, the voltage goes way up, which means that it becomes an even better species for doing this. So most metals get easily oxidized at either of those potentials. And so if you have an exposed metal surface, we tend to see like corrosion on that surface over time, especially if you have two different metals in contact with one another. Any two metals are going to have different reduction potentials. And then if you put in water and salt or water and any sort of acid, there will be a spontaneous reaction that will corrode one of those metals and form an abundance of the other, basically not making the thing that you wish was still made. So people will go to a lot of lengths to make sure that doesn't happen. Painting metal is one of the reasons why we do it, so that we can sort of cover the surface. I grew up with nothing but metal cars, and in wintertime, especially in Chicago, salted roads would make for really aggressive environments on those cars, and they'd be like rusted through. Now most cars are some version of composite or fiberglass, which means that they are protected from that kind of thing. So corrosion is basically the opposite of what's known as the refinement process. The way we get metals at all is you kind of go underground and you grab a chunk of rock that you know contains some metal species there, and you put it in solutions, dissolve it, and then you draw those metals out through a electrolytic process. Corrosion is basically restoring it to that. And so you'll find over time, like everything in nature has sort of like a back and forth way of doing things. I hope that is helpful to you. It's a really interesting chapter to me. The last, I'd say, 5 pages or so of it, it really is just a lot of reading. We're not going to get into the math on electrolysis. It deals with amperage and other things. There's only one lab that might have dealt with it anyway, and I think most of the time they tended not to do that part. So I'm not going to go into it because I honestly think we have plenty of math to do. Don't really need any more. And that's it. Electrolysis finishes out that chapter, and then the next thing we go into, which we do on Wednesday, is nuclear chemistry. And we're really only going to spend one day on that. And I'll talk a little bit about like what the culture for nuclear chemistry has become since I had grown up in this area and watched a few things happen and watched what our power resources are. So don't forget, you have homework due on Sunday, extra credit due on Friday. Your quiz will be on Thursday, and then our exam 3 is scheduled for next week. Okay, so if there are no other questions, I'll stop the recording, post this to the website later,